So now that we've discussed Wittig reactions and how they work in the previous video, let's try to think of how we can use them in synthesis problems. Now when you try to do a synthesis, you can think about the starting material and what you can do with that, or you could also think about the product that you want and how you can work backwards from that and make it. So you could do a forward synthesis or what's called a retrosynthesis, and usually they draw that with a slightly different arrow. Well, let's think about this retrosynthesis for a second. If forgetting about this original molecule, just thinking about how we can make that, now that you know the Wittig reaction, whenever you see a double bond in an alkene, you should think, I can make that with a Wittig reaction. And when you're trying to think of what reagents you need, draw a line through the bond and draw each piece on either side. So, for example, we have this benzene ring and a carbon there with a double bond. And we also, on the other side, just have one carbon with a double bond. And this carbon would have two hydrogens on it. So I've sort of taken the two pieces there and just split them asunder, like that. Okay, now there are two ways you can make a Wittig reaction out of that. You could either have an oxygen on one of those parts of the double bond, or on the other. Now, if you have oxygen on one, then your phosphorus with the three phenyl groups, that'll have to go on the other. So for example here, we could have our phosphorus, our triphenyl phosphine, where each of those pHs are a benzene ring. So we could either have it on the carbon there, or we could have it on the carbon in the ring. So these are our two possible Wittig reagents. If we mixed either of these together, both of them would give us our product. But we want to choose the more efficient one, and because this Wittig reagent is made in an SN2 reaction, where the phosphorus acts as a nucleophile and attacks the carbon, because of that SN2 reaction, we want the carbon to be less crowded. We want it to be less sterically hindered. The fewer carbons are bonded to that, the better for us, because that means the phosphorus will have an easier time attacking it. And that's especially important because this phosphorus is bonded to 3 benzene rings, so it's already really crowded itself. So we want the carbon to not be crowded at all. Now in this case, that carbon is not bonded to any other carbons. In the other case, the carbon that has the phosphorus on it is bonded to one carbon. And because of that, this bottom one is more crowded. It has more stuff nearby that would make it hard for this phosphorus to come in and attack that carbon as a nucleophile, whereas this has very little stuff nearby. And so it's easier for that phosphorus to come in and attack that as a nucleophile. So the Wittig reaction we're going to use is this one on the top, this one here, because we can form that triphenylphosphine. We can have that triphenylphosphine attack the carbon more easily because that carbon is less crowded than the one down here. Okay, well those are our Wittig reagents. Very well. So notice we're thinking backwards here. We started with our product and we said, okay, well if I had this Wittig reagent, I would be able to make that product. But how can I make this Wittig reagent, this 1/2? Now we know how to make this. There's a whole recipe you could use. You just need a carbon with a leaving group and triphenylphosphine, fine. You don't have to include that in your mechanism, in your synthesis, you just need the Wittig reagent. So how can we make this? Well, now you want to look back at your starting material, and maybe then you can see a connection. The only real difference between the starting material and this aldehyde that we want to use in this Wittig reaction is that there is an extra bond to that oxygen. And so really this is an oxidation. It's an oxidation because you're taking a carbon that had only one bond to an oxygen, and you're giving it 2 bonds to the oxygen. So when you increase the number of bonds to an oxygen, That's oxidation. Now here you have a primary alcohol. This alcohol, this OH, is only bonded, is on a carbon that's only bonded to one other carbon. So it's primary. And if you ever want to turn a primary alcohol into an aldehyde, you have to use a weak oxidizing agent. Excuse me, the weak oxidizing agent that you want to remember is PCC. It's pyridinium chlorochromate. Those chromium reagents tend to do oxidations, and in this case, this is relatively stable. It's being stabilized by a pyridinium ion, the chromium species. And so, because it's relatively stable, it only oxidizes that alcohol to an aldehyde. If you were to try to do that same reaction, if you were to do this one with the same primary alcohol, and you were to treat it with a strong oxidizing agent, like sodium dichromate, and you usually do that in an acid wash, so sulfuric acid and water, in that case, it would oxidize it all the way to a carboxylic acid. You would have that oxygen, or this carbon here, bonded to oxygen 3 times. So we don't want a carboxylic acid, and we saw this reaction actually. We saw something like this, where you oxidize the carbon on the benzylic position, you get a carboxylic acid with these strong oxidizing agents. So if you just want to stop at the aldehyde and not go all the way to the carboxylic acid, then you use a weak oxidizing agent, you use PCC. So that's our synthesis. Overall, we will take our primary alcohol, we'll use PCC, that will turn that primary alcohol into an aldehyde, and all we have to do is combine that aldehyde with our Wittig reagent, and we just note the carbon that we want to attach to that. It's just a C carbon with 2 H's. And that would give us our product. The oxygen ends up getting replaced with the double bond to a carbon, and the that has the 2 H's on it. Okay. Now, let's try this one. Okay. Again, you can do the forward synthesis, or you can do the retro synthesis. You can start with the reactant and think, how can you go forward to the product? Or you can start with the product and think, how can I work backward to the reagent? In this case, it's useful to look at the product because you'll see this ketone. You'll see this alkene. And now that you know about the Wittig reagent, anytime you see an alkene, you should think, oh, I can make that with a Wittig reagent. And that should be especially clear if you compare the reactants and the products here, because you'll notice that the products have an extra carbon. This carbon in the top right is not in the original molecule. So you form a new carbon-to-carbon bond. Not only that, but you form a carbon-to-carbon bond that makes an alkene. So that's like a textbook recipe for the Wittig reagent. So if we wanted to make that, what Wittig reagent would we use? We'll draw a line through the double bond and draw the 2 pieces in the double bond separately. So for example, we have that 6-membered ring, the cyclohexane, and then I'll draw a double bond, and then I'll draw the other carbon also in a double bond. So I've taken this, and I have these 2 pieces, the ring and the carbon. Oops. Okay, well, we can think of this twice. We need to consider this twice, because when we're thinking about what Wittig reagents we need, we could have the oxygen, we need a ketone and the triphenylphosphine, the Wittig reagent itself. So we could either have the ketone here on the purple part or on the green part. And whichever one has the ketone, the other one will have the phosphorus bonded to 3 phenyl groups, 3 benzene rings acting as branches. So those are our 2 possibilities. When you're trying to choose between them and think about which one is better, you want to look at the carbon that's bonded to the phosphorus and ask yourself, how crowded is it? This carbon on the left, that is bonded to 0 carbons. That has 0 carbons bonded to it. The carbon that's bonded to the phosphorus on the right is bonded to 2 carbons. So the one that's bonded to more carbons is more crowded. And so that is actually worse for us, because the phosphorus has to attack that carbon through an SN2 mechanism. And the SN2 mechanism is harder when you have a crowded, when the leaving group is attached to something that's crowded. So the Wittig reaction we want to use is going to be the one on the left here. Oops. So this. Okay. Well, if we had those reactants, then we could make this final product. But how can we turn this starting material into this ketone? Well, one thing you'll notice when you compare these is that this starting material has no oxygen, and this ketone has an oxygen. So we have to add an oxygen onto this molecule. In other words, we have to do an addition reaction. Well, how can you add an oxygen onto an alkene? There are a couple ways. You do any type of hydration. In Organic Chemistry 1, you would have learned 3 of those. The first one would have been acid-catalyzed hydration. And that's really cheap and really easy. You just need water and acid. And that adds an H and an OH onto the 2 carbons in that double bond. You would have learned 2 others, oxymercuration demercuration, which also adds an H and an OH, and hydroboration oxidation, which also adds an H and an OH. The 3 reactions were different in their type of details. This acid-catalyzed hydration, it's a nice choice because it's inexpensive and it's environmentally friendly and it's not deadly. It's not really toxic. So it's a nice choice in that sense, but it had some difficulties in the sense that you could get carbocation rearrangements, and also it was Markovnikov addition. So if you didn't want Markovnikov addition, then you wouldn't do this. Now, if these terms are unfamiliar to you, let me know and I'll send you links to videos from Organic Chemistry 1 on these topics, on doing these addition reactions. For right now, we don't care about carbocation rearrangements. We wouldn't get any on this molecule because both of the carbons in the double bond are secondary, and both of the carbons nearby are secondary, so there's nowhere for a carbocation to rearrange to. So it's a great choice to do this very inexpensive and non-toxic hydration reaction. So if we do this, then we finally get our oxygen there. And all we have to do to get from this alcohol to this ketone is an oxidation. Since it's a secondary alcohol, this carbon that has the OH on it is bonded to 2 other carbons, so it's secondary. Since it's a secondary alcohol, we don't have to worry about using PCC, pyridinium chlorochromate. We used that in the previous example because we had a primary alcohol. Our alcohol was only bonded to 1 carbon. So we used PCC to bring it to the aldehyde. But now we have a secondary alcohol. The carbon that has the OH is bonded to 2 other carbons, and so we can use an easier oxidizing agent, something like sodium dichromate. Okay, so here's our thinking. Let's draw it out all just in step by step. So we have cyclohexene. If we do acid-catalyzed hydration with that, so water and acid, then we end up adding an H and an OH onto the two carbons that were involved in the double bond. Notice that if I had switched these, if I had put the OH on the left and the H on the right, all you have to do is flip this molecule over like you're flipping a pancake, and you'd end up with this. So it doesn't matter which goes to which in this molecule because there's symmetry in the molecule. So you do an acid-catalyzed hydration. Once you have the acid-catalyzed hydration, you can do an oxidation with sodium dichromate in water and acid that turns the alcohol into a carbonyl. And once you have the carbonyl, you just have to treat it with the right Wittig reagent. And the half of your Wittig reagent that has the carbon on it, that will end up replacing the oxygen. So you get that. Notice this on the end is a CH2. And so that three-step synthesis gets the job done. You end up going from cyclohexene to this six-membered ring with an alkene coming off of it. So as you're doing these syntheses, remember if you ever get stuck going in the forward direction, if you don't see the path that way, try to work in reverse. Look at the product and think, okay, ignoring this reactant, how could I make this product just knowing the reactions I know? And that process of thinking that way is called retrosynthesis. So always consider that as an option. Otherwise, the patterns you'd want to see here is converting from alcohols to carbonyls. We used PCC and we used a strong oxidizing agent like sodium dichromate. Using Wittig reagents to turn carbonyls into carbon-to-carbon double bonds. And doing addition reactions just to get the original alcohol on the molecule. And those are some principles that you'll see involved in these multi-step synthesis problems where you use Wittig reagents.